Hello everyone, in this video we'll be discussing the exam 4 review for Math 130, which is an intermediate algebra at Long Beach City College. And the first question, so there's 10 questions in the review. And the first question here is to solve the following quadratics by the stated method. So here, for this one, I asked to do it by completing the square, and for the one below, I asked to do this by quadratic formula. Okay, so the first thing to notice is that, first off, these methods are pretty different. But for quadratic formula, we need it to be in the form we actually have for A, and for completing the square for part A, this form is okay, but really what we care about actually for completing the square are just the x squared and x terms. We need to make sure there's no number in front of x squared, which there isn't here, so that's good. And what we're going to take advantage of is this fact of completing the square. So I used CTS for shorthand for completing the square. And that is that if you have x squared plus bx, there is a magic term which allows you to write this as a square, as a completed square. And the completed square will be x plus b over 2. And this makes sense because if you actually fill this out, you get x squared plus 2 times their product will be bx exactly, because 2 times b over 2, the 2's cancel, so you just get bx. And the last term is this one squared, which is b over 2 all squared. So this magic term ends up being half of the middle one squared, half of the middle coefficient squared, but only when there's no number in front of x squared. Now if you do have a number in front of x squared, just divide through by the number. So for example, if there was a 2 in front, divide everything by 2. You'll have fractions, but the idea here still holds. So let's see. So what I want to do is I want to get these two by themselves first. So I'm going to add that 5 to the other side. And I'm going to prepare for completing the square by adding some mystery term to both sides, as well as adding that 5 to the right side. So this mystery term we just said is half of the middle term squared. So if you half this middle term, that's 3 over 2, all squared, ends up being 9 over 4. So I'll write it as 9 over 4 here. Now here it doesn't actually matter because we're just adding it to this side so that it is now a completed square as x plus that number, which is 3 over 2 before squaring, and then all squared. And again, you can FOIL this out to see that it indeed gives you the previous line on the left side. Okay. But now here, 5 is 5 over 1. I know that's really 20 over 4. You multiply top and bottom by 4, you get 5 times 4 on the top, which is 20, so it's 20 over 4. Added to 9 over 4, it gives us 29 over 4. So the right side, we actually do need to add 9 over 4 so we can combine them. But on the left side, I'm just using it to write this as a completed square. And now what I want to do is get rid of this square by square rooting both sides, but when we do this, we see this property that very often people forget, and it is called the square root property. And it basically says that if you have a square equal to a number, the inside, the original thing that was being squared, could be positive or negative. So we get this special plus minus symbol, which tells me that this really breaks into two solutions. Now, this is kind of a weird, I guess, example of that, but just to show an example of that so you believe me that this is true, let me erase this, is let's say x squared is equal to 9. This means if you square root both sides, you get x is equal to the square root of 9, which is 3. But from the square root property, this says that it's really plus or minus 3. Now, the reason why is because if you square 3, you get 9, but if you square negative 3 times negative 3 is positive 9 still. So positive and negative 3 both do the trick, actually. So in general, we get that plus or minus when you introduce your own square root. Okay? So now on the left side, we have this x plus 3 over 2 without the square now. Good. And now we have this plus or minus. Now I can square root the top and bottom individually. The square root of 29, nothing interesting happens. But the square root of 4 is just 2. Now, you want to make sure to simplify radicals when you can. So for example, with the numerator, 29 is a prime number, it doesn't factor. But something like the square root of 24, for example, maybe that's not the best example, but 24 is 4 times 6. And if you split this up, which you can do with radicals, the square root of 4 is just 2. And we saw that actually in the last exam, in the exam review as well. We're almost done. The last thing to do now is just to subtract this 3 over 2 to the other side. So we get x is finally negative 3 over 2 plus or minus radical 29 over 2. And then maybe the last thing you can do if you want, which is not totally necessary, but I think it's a lot of fun to do this, is to combine these all under the same denominator because, of course, they already have the same denominator, which is nice. Now the beauty of this is, even though I didn't ask you to do this by any other method but completing the square, if you find quadratic formula easier, and most people do actually, you can actually apply quadratic formula to this and see that you get this to kind of check your work, I guess, in some sense. But I still want to see, of course, you do it by this method. So off to the side, if you want to just do quadratic formula real quick and verify that that is what you get as well, that should reinforce your knowledge on the fact that this is the correct answer. So checking your answer, basically. And notice these are two. There's the plus one and then the minus one. So those are two answers in one, written with that plus or minus symbol, which is fine. Okay. Now for this one, again, we want it in this form where everything's on one side and 0 is on the other. So this 3x, I'm going to subtract to the opposite side. And I'm going to stick it in between these two terms so that we have this polynomial in descending order. X squared, then x, then constant. And from the setup for a quadratic formula, this is a, which is in front of x squared, b, which is in front of x, and c, which is our constant term. So quadratic formula needs this form. That tells you what a, b, and c are. So you can't just say this is a, b, and c, or this is a, that's b, and that's c. They have to be on one side and 0 has to be on the other. Okay, so maybe I should just write that down real quick just so we know what the quadratic formula specifically says. I'll write QF for short. And it basically says that if you have the quadratic equation ax squared plus bx sorry, but there's a little bit of moisture on the board, plus bx plus c equals 0, then x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Now that's what we're going to be using here. So this is the quadratic formula that you should know. Most people just remember this bottom part, but it's important to know this as well. This tells you that the setup has to be so that everything is on one side, is zeros on the other, and it tells you what a, b, and c specifically are. Okay? And I guess I should box the completing the square, because it's kind of like a formula that we ended up using here. Okay, so I'm going to use these a, b, and c values. Now notice that I've emphasized here that b is this negative number and c is a negative number, because these are pluses. So if there's a sign in front of the number, that's part of that letter as well. Okay? So let's just set it up directly. It's going to be x equals negative b, so negative 3, plus or minus the square root of b squared, it's negative 3 quantity squared, minus 4 times a times c. A is 6, c is negative 4, all under that radical. And this is all over 2 times a, which is 6. Now it's important to know it's all over. For some reason, I've seen students write the over part only after the radical for some reason. I don't know where that came from, but I've seen it quite a bit. But this is how you do it. Now double negative here is positive, so that's going to be positive 3, plus or minus the square root of, let's try to compact this all together. So negative 3 squared, that's 9, positive 9. We actually saw that above, which is funny. This was a side note, by the way, so I'm just going to box that so it doesn't get in the way of the word. Double negative here is going to be positive, so that's kind of interesting. Okay, 4 times 6 is 24. 24 times 4, that's 96. Okay, and 96 added to 9 is actually 105. Now 105, you can try to factor it to maybe break the radical. I don't know if we'll have some success in that or not, but I know it's a multiple of 5 because it ends in a 5. And it's actually going to be 5 times 21. Right, 5 times 20 is 100. 5 times 1 is 5. So it's 100 plus 5. But since 21 is 3 times 7, this is 5 times 3 times 7. So there's no repeat in that factorization. So what that tells me is that if we try to break this up, there's no square. Like we saw here earlier for the square root of 24, we broke it up into 4 times 6. 4 was a square. But 3, 5, and 7, they're all prime numbers. There's no repeat there, so you can't write it as a square in the product. So this unfortunately doesn't break. Okay. And this is all over 2 times 6, which is 12. Now, it's very tempting, I guess you can say, to cancel these 3 and 12 a little bit. But you cannot do that unless this term also gets a hit of that cancellation. And in this case, it doesn't. If something broke out of the radical and it was also a multiple of 3, then you can cancel 3 in the numerator with both of these terms and with the denominator. So the way you would normally show that is either by splitting this up into 2 terms, kind of like the reverse of this action, and then see cancellation with each one. So if you want to see that, I mean, I guess I could show it over here. So that's 3 over 12 plus or minus radical 105 over 12. There's no cancellation with the second term, but there is with the first one. So you could write your answer like this, I guess, but I honestly think it's better just to write it like we had it initially. Now, if the radical does break and you have something coming out, I would like you to, instead of splitting it up like this, which you could do, I would like you to factor whatever they have in common out. So if a 3 popped out of the radical, for example, you can factor the 3 out of these two terms, cancel that 3 outside of that product with the 12. That's how you do that cancellation, not through the sum. Okay, okay, great. So that was A and B for part 1. So that was part 1, or number 1. So now let's move on to problem number 2 now. All right, so this problem number 2 here asks us to solve the following by any method. Now, the reason why it says any method is because these problems, kind of spoiler alert, but they'll basically reduce to quadratics, like we saw with 1. But with problem 1, I specified what method to use, completing the square for part A and quadratic formula for part B. For all I know, factoring would work here, or you can use quadratic formula or completing the square. Those methods are still valid. So here I just don't specify which method to use. You can use any method. So let's take a look. For number 1, or for part A, I should say, I want to find the least common denominator and multiply through by that first, and then we may see that quadratic happening. What you can also do actually is you can combine these two into one by finding the common denominator into one fraction and then cross multiply. That works too. But I'm going to find the LCD. Now the LCD here is actually going to be, let's see. Well, we need x from this denominator, x plus 2 from that denominator, and we actually also need a 4 from this denominator. So let me sneak that 4 right there. Okay. Now, what I want to do is I want to multiply each of these terms by this least common denominator and basically filter out these denominators from our expression, so our expression now will have no fractions. So here, if you multiply this, we're multiplying everything by the LCD. So multiplying this by the LCD, the x's cancel, so the top one is only multiplied by what doesn't cancel, which is just 4 and the x plus 2, because again, the x's will cancel out, they cross cancel. Here the x plus 2's cross cancel, so here we're multiplying the top 1 by that 4 and that x, only the x plus 2 cancels out. For this third one, the 4 cancels, so the top 3 is only multiplied by this x, not the 4 cancels out, and then x plus 2. So we end up with this, and it may not seem apparent at first, but this is a quadratic equation. Let's distribute and try to simplify as much as we can. So we have 4x plus 8 plus another 4x plus, or equals a 3x squared plus 6x. Now I want to move everything to one side so the zeros on the other. These combine to 8x. So I'm going to continue over here up on top. So I'm actually going to move everything to the right because the x squared term here is positive and I want that to be positive just for simplification. We're going to have 0 on the left. Let's see if you can follow me. So we have 3x squared on the right. These two combine to 8x, but then I'm going to subtract the 8x over here. So that'll cancel these two because we're subtracting 8x, since 4x plus 4x is 8x. Subtracting 8x to the other side will cancel those once combined. And then I'm also going to subtract this 8 to that side. That'll cancel this 8. So on the left, we only have that 0. Okay? But on the right, we have 6x minus 8x, which is negative 2x, and then minus that 8. Okay. Now, we could actually solve this by factoring, and I'm going to do it that way, actually. I'm going to use this technique I like to call the super x method. It has to do with what is called the AC method, where you multiply a and c. Kind of think of ax squared plus bx plus c, like we had in quadratic formula. So AC will be negative 24. So the super x method allows us to multiply to that number, but then add to the middle number, which is negative 2. And the two numbers that do this are 4 and 6. To make the signs work out, it's negative 6 plus 4. And the reason why we draw this line on top is because the number in front of x squared allows for a 3x on top of this. So the reason why I call this super x is because with just the x method, or the x diagram, you don't usually have those, and the answer is just x minus 6, x plus 4. But in this scenario, because there is a number in front of x squared, we need to have representation of that somehow. We do it like this. And then from here, we look to see if there's any cancellation seeing these like fractions. So this one doesn't reduce as a fraction, but this one does. You can divide this by 2, or actually by 3, excuse me. and you get x over negative 2 after reduced. So now these fractions convert to binomial factors as 3x plus 4 for the first one, from this guy, and then this would correspond to x minus 2. So you can actually check it when you fill this out, it indeed works. So there we go. But now, because they're equal to 0, we have this property that tells us that if you have a product of two things at 0, one of them must have been 0. So either this is 0 or that's 0. If 3x plus 4 is 0, that means x is equal to negative 4 over 3. And if x minus 2 is 0, that means x is equal to positive 2. Now, if that was too hard to follow, you can just actually write 3x plus 4 equals 0, x minus 2 equals 0, solve those off to the side. But the way I see it, if x minus 2 is 0, you just add it to the other side, so it's a sign change, basically. And same thing here, if 3x plus 4 is 0, subtract 4 to the other side, that's a sign change of that. But then in addition, you have to divide by 3 to get x by itself. So you end up with negative 4 over 3. Okay. Now, the only issue, so this is basically solving the quadratic, but the only issue with the entire problem is that we must check for extraneous solutions. Now, when you have problems that involve denominators or problems that involve radicals, you must check your answer. You must check your answers in this case. Now, the one I know will not work. Actually, I'm sorry, they both work. But if this was an x minus 2, that 2 would not work because it would result in a 0 denominator. Okay, but in this case, they actually both work, and you can verify that on your own. The negative 4/3 is going to be hard to check because it's a fraction, so I'll allow you to do that on your own. For the 2, I'll just check kind of verbally. 1 over 2 plus 1 over 2 plus 2 is 4. So 1 over 2 plus 1 over 4, that's a half plus a quarter. That is obviously 3/4. So 2 works, and again, it'll allow you to check the negative 4/3, which is less obvious because it's a fraction. But it'll allow you to check that on your own. These both work. But again, it's important to check that you don't have any 0 denominators. And in fact, maybe I should have stated here that because of the LCD and because of these denominators, none of these factors can be 0. Of course, 4 is never 0, so that's fine. But x cannot be 0, and x plus 2 cannot be 0. But notice x plus 2 is 0 only when x is negative 2. So we must kind of reassure ourselves that these don't pop up in the solutions, which I thought they did at first because 2 looks like negative 2, obviously, but this is x plus 2, not x minus 2. So we dodged a bullet there. So now for B is kind of interesting because we could solve it in the usual way we solve radical equations, which is by isolating the radical and then squaring both sides. And I'll allow you to try that on your own and see if you get the same answer I'll get here. But what I'm going to notice is something that's not super obvious at first glance, and that's that this is what is called quadratic form. So it looks like a quadratic, but it's not a quadratic. So we can do this through a substitution. I'll call the substitution t. And basically what I want is I want the square root of x to be equal to t. So that way, if you square both sides, you get that x is equal to t squared. So that replacing x with t squared and radical x with t, this now turns into a quadratic. And this can actually be factored pretty easily, just using this kind of x method diagram. The two numbers that, I should have a plus up here, but the two numbers that multiply to positive 2 and add to the middle negative 3 are, of course, negative 2 and negative 1, just like that. And they multiply to this and add to this. Good. So that means this factors as t minus 1 times t minus 2. And then by that property we used above, these two things multiply to 0, so either t minus 1 is 0 or t minus 2 is 0. So that means if you sign change those, you get t is either positive 1 or positive 2. Okay? But remember what t was. So we're done solving for t, but not for x. So in this substitution, our original value for t was radical x. So I'm going to back substitute now. This tells me that radical x is either 1 or radical x is 2. Now, if you square both sides for each of them, you get that x is 1 squared or x is 2 squared, which is 4. And now we have to check these in the original to make sure it works out. Now, when you plug in 1, 1 and radical 1 are both 1. So it's 1 minus 3 plus 2, which is negative 2 plus 2. That is 0, so that works. Okay, when you plug in 4, there's going to be 4 minus 3 times radical 4. That's 3 times 2. That's negative 6. 4 minus 6 is negative 2 plus 2 is still 0. So they both actually work. So instead of writing it like this, which you could if you wanted to, I'll still box it, I guess. But for whatever reason, I just prefer to have it like a comma separated list. X would be equal to 1 comma 4. I don't know why I prefer that, but I just think it looks a little neater in my opinion. But this is fine too. Great. So that was a nice citing of the substitution method here. Great. So now moving on to number 3. All right, so for number 3 here, we're asked to find the vertex and axis of symmetry for the graphs of the following functions. And these, of course, are quadratic equations, so their graphs are parabolas. And parabolas have a vertex and an axis of symmetry. Now, axis of symmetry, which I very often use the acronym AOS for, is kind of, I don't know, this is kind of me testing you on the vocabulary of things. Because once you know the vertex, the axis of symmetry is free, provided you know what's going on. So just to give you an idea, if you have a parabola, whether it opens up or opens down, doesn't actually matter for our purposes here. The vertex is going to be this kind of bottom point. It's the most end point of the parabola. Okay? And the axis of symmetry is actually the line that passes through this point. So in this case, it's a vertical line, of course. Okay? And notice a vertical line always has an equation x equals whatever x value it passes through. But you usually, by the way, label the vertex as h comma k. So if, let's say, the xy plane is here, then, of course, this vertical line is going to pass through the x value of the vertex, which is x equals h. So the equation of the axis of symmetry is just x equals the x value of the vertex. So once you find the vertex, the axis of symmetry is just free. Okay, but again, provided you understand that, otherwise you won't know what's going on. Now, how do you find the vertex? Well, there's actually a few ways, and I want to show 2 different methods. I'm going to show, I'll do this. I'll show completing the square method here, and I'll show the formulaic way over here. Now, the completing the square method kind of all hinges upon the fact that any quadratic equation, ax squared plus bx plus c, has a graph that is just a transformation of a parabola, just the parabola x squared actually, by shifting over h units either to the left or right, and then k units either up or down. So depending if k is negative or positive, and h also is negative or positive, and also depending what a is also, that actually plays a factor. But long story short, it ends up looking like this. A times x minus h, all squared plus k. So I know it may look like a little overwhelming. Normally I call the first one standard form and the bottom one here vertex form, because it tells you the vertex hk. This is all in terms of the vertex components h and k. Now how you get from here to here is by completing the square. So I'm going to show that here. But notice to complete the square, we want to isolate the x squared in x terms like we saw with problem 1 today. And to do that, I need to get rid of this 3 as well, because we don't want a number in front of the x squared term. So what I'm going to do actually is I'm going to pull out that 3 like this. Now also I want to add some mystery term to this to make this a completed square. And I'm going to also notice that if you half this negative 2, you get negative 1, so it's x minus 1 squared. So when you FOIL this out, this will be, well, x squared minus 2x plus 1. So this mystery term is actually a plus 1. Okay. Now, that was only considering these two. But now, think of what happened here with the plus 1. Well, we're bringing this 1 in out of nowhere, so we better get rid of it as well as subtracting it so that we end up with nothing. That's equivalent to adding that number to both sides. The only issue is that this 3 will actually distribute and make that a 3 actually. Not a 1, but a 3. So instead of subtracting 1, I'm going to actually subtract this 3. Now if that looks strange at first, these will combine to negative 2. And then after distributing that 3, 3 minus 2 is that 1 we had there. And these two combine to negative 2 on the outside. So if you actually FOIL this out, distribute the 3, and then combine the constant term with negative 2, you will exactly get these 3 terms. So it is the same. Okay, I haven't pulled anything crazy up my sleeve. But what is kind of crazy is that already we're in the vertex form. And we can tell right away that the vertex is h comma k. h is what's subtracted from x inside of the parentheses, so it's a sign change of the number next to x, that's positive 1, and the number added to the square term, which is negative 2. So that's the vertex, and the axis of symmetry just has the equation x equals the x value of the vertex, which is 1. So that's it right away. So that's the power of vertex form. Gives you the vertex right away, and the axis of symmetry is just x equals whatever the x value of the vertex is. Okay. Now, what about, I mentioned there's a kind of a formula. So what about the formula? Well, as it turns out, actually, h can be written as negative b over 2a. And if that doesn't look familiar to you, it should. It's actually part of quadratic formula. If you ignore that plus or minus radical part, you end up getting just this. And it's kind of hard to explain, but long story short, if you look at parabolas, there's symmetry about this point h, right? So think of the plus or minus as adding or subtracting x values from this point to get around that h value, or around this x value, h. That's one way to kind of think of it. So if the radical is 0, you're kind of stuck in the middle of the parabola, and you have no partner on the opposite side. That's basically what's going on. Now, with that being said, to find k, all you need to do is plug h back into f. So h is this, and k is just f of h. So plugging h in, you get k. Now, why is that true? That's true because, well, k is the y value, and since we have a function, we can plug h back into this to get the corresponding y value that corresponds to that x value at that function when you plug it in, basically. So here, we have a, we have b, we have c. Let me label those. A is negative 2, b is negative 3, c is positive 2. So a, b, and c. We don't even need c, actually. We just need b and a for h, right? Okay. So h is then going to be negative b, negative 3, over 2 times a, 2 times negative 2. Okay, so it's a triple negative. Double negative on top is positive. Negative on the bottom is a negative, so it's going to be negative 3 over 4. So h is negative 3 over 4. That's the first step. Second step is to find k, and you plug this value back into f, or in this case g, that's our function, to find k. So in this case, k is equal to g of h, which is negative 3 over 4. So plugging it in, with a little bit of patience, we can make it. Let's see. Everywhere I see an x, replace it with negative 3 over 4 in parentheses, and then just kind of do some number crunching. So when you square this, square top and bottom, negative squared is positive, so it's negative times positive 9 over 16. Double negative here, that's 9 over 4. If you multiply, think of that as 3 over 1, multiply across, you get 9 over 4, plus 2. Okay, there's cross cancellation here, 2 goes into 16 8 times. So this ends up being negative 9 over 8, okay, plus 9 over 4, but if I multiply top and bottom by 2 to get a common denominator of 8, that's 18 over 8, okay, and 2 technically is 2 over 1, right? So if you multiply top and bottom of this by 8 to, again, get that common denominator of 8, that becomes positive 16 over 8. So combining these, negative 9 plus 18 is 9 itself, so that's 9 plus 16, which is 25 over 8. And that doesn't reduce, so we have k is equal to 25 over 8, and now we have h and k, so altogether we can say that our vertex is the point negative 3 over 4, comma, 25 over 8, and let's not forget about the axis of symmetry, which is just x equals the x value of this vertex. So the axis of symmetry here is x equals negative 3/4. So imagine trying to do this by completing the square, probably pretty nasty, and I'm assuming that's because we have these fractions, but I encourage you to try it on your own. And also you can try this method here as well. Maybe you think this method is easier than completing the square. Maybe I'm biased, but I'm making it seem like completing the square is the way to go. So now moving on to number 4. Okay, so for number 4, I don't really give super specific instructions. I just say to solve these inequalities. Now, I would prefer you to write your answer in interval notation, and in fact, I don't know how you would do it otherwise. I mean, you could write your answer in maybe set builder notation, but the method we usually use to solve these nonlinear inequalities gives you the answer like straight up in interval notation. So let's see what that's all about. So the first one is a quadratic inequality, and the second one is a rational inequality. Now, for a quadratic inequality, there's basically 3 steps. The first step is to solve the related equation, which is y squared minus 5 equals 4y. So imagine this is equality, solve that. So this is a quadratic, we have to move everything to one side. I'll subtract that 4y to the left. We get this. This actually factors as, I guess, 5 and 1. You can use a diagram to help you out with this, but it should be negative 5 and positive 1. Those add to negative 4 and multiply to negative 5. So then by setting each of these equal to 0, your y is equal to the opposite signs of these numbers, which are positive 5 and negative 1. So that's step 1. Once you have step 1, then step 2, what it does is it allows you to plot these on the number line and then pick test values around these values on the number line, between negative infinity and infinity, of course. So in order, we have negative 1 first, from left to right, and then positive 5. And of course, there's no scale here, just writing the numbers on the number line. And now I want to test numbers in between. So what numbers I'm going to pick here, here, and here? Well, a number in between negative infinity and negative 1 that I think is appropriate is negative 2. Here 0 works, and here 6 works. Any number will work, though. It's just a test number. It's just checking to see whether the inequality is valid for that number, and that represents the entire section. Now, speaking of which, I'm going to write these sections in interval notation, and I'm not going to include the endpoint, so I'm going to write open intervals. Even though this inequality may be closed, and here it is, and here it's also closed, you may have brackets in your answer, basically. But here I'm going to write the open intervals. So this is the interval negative infinity to negative 1. This is the interval negative 1 to 5. And this is the interval 5 to infinity. Perfect. So now testing these, let's take a look. It's honestly best, this is a little strange, but it's honestly best to do exactly what we did here, but keep the inequality symbol. So notice, if you just subtract 4y to this side and factor this symbol will still be greater than or equal to. So actually, if you imagine that this is like this, so imagine this is a greater than or equal to, it's better to do it that way, actually. And the reason why is because when you test, you're just checking for the sign. So when y is equal to negative 2, we get negative 2 minus 5, that's negative 7, so it's negative. And negative 2 plus 1 is negative 1. So all I see are the signs. When you plug in negative 2, you get negative, negative. And negative times negative is positive, so that checks out because it is bigger than 0. Now, if you test it with the original inequality, it'll still work, but it takes a little more time to see that. It's better to take advantage of the factored form we have, provided the inequality symbol hasn't changed or anything like that. So you can kind of mix, I guess, solving the related equation to getting this in the form where 0's on one side and everything's factored first, and then from there solve the related equation or something like that. But I hope that makes sense. So that means negative 2 actually works. So this checks out. Let me do that in red. Good. So we're going to select this, this interval. So I'll do that in a moment. 0, and again, you can check here. It's not that bad. When you plug in 0 here, you can clearly see 0 minus 5 is negative 5. And that's 4 times 0 is 0. Negative 5 is not bigger than 0, so that doesn't work. Also plugging it into the factored form, 0 minus 5 is negative. 0 plus 1 is positive. Negative times positive is not bigger than 0. It's less than 0. It's negative. So it's how quick it is to just check with the sign when you have things factored. Okay. Plug in a 6. We get 6 minus 5 is positive. 6 plus 1 is positive. So positive times positive is positive. This will work. Plug this in here. Get 36 minus 5. That's 31. And that's 4 times 6 is 24. And clearly that does work as well. So I'm not picking this one, but I am picking these two. So now step 3 allows us to get the intervals that checked out, take their union, and change any of the parentheses to brackets as needed. So since this is or equal to, that will happen. And in fact, the related equation tells us which values worked. So 5 works and negative 1 works. So those will actually be bracketed. So let me show that right here in step 3. That'll just kind of build our answer. So negative infinity, negative 1, bracket, union, bracket 5 to infinity. That does it. Now, why did that work? Why are these bracket all of a sudden? Well, it's because since it's or equal to, 5 is allowed to be, well, y is allowed to be equal to 5 and y is allowed to be equal to -1. If you plug them in, you'll get equality. Now, since it's greater than or equal to, this is basically two equations in one, or an inequality and an equation in one. So the inequalities will be solved with the open ones, the open intervals, but then considering the fact that when it is equality, you get these solutions, those should be included in our solution set. So to include those, we'll make those parentheses a bracket, meaning that we have possible equality at those values. Okay? Now another way of doing this is by graphing. It's kind of interesting, but if you were to actually graph this, I guess you'd have to, again, move everything to one side so the zeros on the other. And if you were to graph that quadratic, you essentially, long story short, get this. It's a parabola that passes through the x-axis at -1 and 5. And I'm kind of looking at it like this. If you move everything to one side so the zeros on the other, you get that parabola must be greater than 0. In other words, y values must be greater than 0. Now, it's a little tricky here because my variables are y, so that I guess would be the y-axis, and this would be the x-axis, or whatever you want to call it. So it looks a little weird like that. But the whole point is that since it's greater than or equal to 0, we want this whole thing to be above this axis. So right here it's below, and here it's above. So from here to here, and from here to here. So that's exactly this, but an interval notation. -infinity to -1, or 5 to infinity. So that's a nice graphical interpretation of that. So that ties in parabolas, so that's nice. Moving on to part B. It's pretty much the same thing, only we also have to set the denominator equal to 0, and that actually becomes representative in step 2 as a possible divider of these areas. So we'll see that right now. So let me maybe start here. So step 1 is to solve, it's kind of a twofold thing. So we're solving the related equation, and we're also setting denominator equal to 0. Now what's interesting is that when you solve the related equation, x squared minus 2x minus 8 over x minus 1 is equal to 0. That's the related equation. A fraction is 0 only when the top is 0. So this just implies that x squared minus 2x minus 8 is 0, and that actually factors as x minus 4 times x plus 2 equals 0. So then we can say that x is equal to the opposite signs of these, which are positive 4 and negative 2. Okay? But another part of step 1, because there's a denominator here, is to also, so let me say and, set the denominator equal to 0 and solve. And solve. So the denominator is x minus 1. So when that's equal to 0, right away we get x is equal to positive 1. Now, some kind of technicalities happen when this is already representative here, but it's nothing too crazy. You can still test things around and you'll kind of see what's going on. So again, there's no real super issue there, but you can kind of try to make up a problem that happens. That probably won't happen though. So here we have now step 2 is creating this number line with these numbers in mind. Not just the ones where equality happened, but also where the denominator was 0, in order. So -2, then 1, then 4. Okay? So from negative infinity to -2 to 1, and then to 4. And again, there's no real scale here. This looks more or less correct, but it's maybe coincidence. So I want to test numbers in between these that are appropriate. Here, here, and I guess here as well. So between -infinity and -2, we can pick -3. Here we can pick 0. Here we can pick 2. And here we can pick 5. Now the intervals are -infinity to -2, -2 to 1, there we go, and then 1 to 4, and finally 4 to infinity. Perfect. And again, writing them as open, we'll consider the closed brackets in a moment. So let's plug these in. Now again, it's best to have things factored. So what I'm going to do, I'm going to border this off so I have some space here. I'm going to do ourselves a favor. I'm going to write this with everything factored. So the top we saw factors as x minus 4 times x plus 2. The denominator is just one expression like that, so we don't need to do anything with that. It's kind of already factored, I guess. And now when x is equal to negative 3, that's negative 7, negative 1, negative 4. So they're actually all negative. So negative times negative on top is positive, divided by negative is negative. So that works because we want to be less than or equal to 0, which basically means we want to be negative. So this works. When you plug in 0, 0 minus 4 is negative, 0 plus 2 is positive, so on top it's negative. 0 minus 1 is negative, so negative divided by negative is positive, so that doesn't work. We want to be negative. To be less than 0 means to be negative. Okay. When you plug in 2, 2 minus 4 is negative, 2 plus 2 is positive, so negative on top. 2 minus 1 is positive, negative over positive is negative, so that works out. When you plug in 5, the top is positive, the bottom is positive. 5 minus 4 is positive, 5 plus 2 is positive, 5 minus 1 is positive. So positive over positive is positive, not negative, so that doesn't work. Now, it will not always be the case where you have alternating yes, no's. It seemed like that was it here, but it's not always the case. It's usually the case, actually, but not always the case. So I'm going to select these two, and not these two. Union those, and then we'll check for equality right now. So step 3 is just building our answer in implementation. I have negative infinity to negative 2, union 1 to 4. Now, the infinities will always be open. You can never be equal to infinity. It's just an idea, really, not even a number. Now, the ones that you can be equal to are where you had equality. The one you cannot be equal to is the one that gave us a 0 denominator, because plugging it in will give you an undefined value, right? So 1 we can never be equal to. The other ones, negative 2 and 4, you can be equal to, and that will actually result in equality. So this is the answer. So long story short, if it's or equal to, you bracket everything if there's no denominator, and you bracket everything except for the one that came from the denominator being 0. Okay. So now moving on to number 5. Here we're given these two functions, f of x and g of x, and then it'll remain true for all 4 of these parts. And then we are asked to find these combinations of these functions. And here I'm asking you to add them, multiply them, and then here we're asked to compose them in some order. So really what you can do is you can actually add f and g together and get a new expression and then plug in 2. But the definition of this really is f of 2 plus f of g, or plus, sorry, f of 2 plus g of 2 is what I meant to say. So if you wanted to, again, you can add these functions together first, then plug in 2. Or, according to this definition, you can actually plug in 2 first and then add them. That's what I'm going to do, actually. So we plug in 2 into this, we get 3 times 2 squared minus 9 times 2. Plus, if you plug 2 into that one, you get 3 times 2. Now, you can kind of see that if you were to add them together first and then plug in 2, it ends up giving you the same thing. You can kind of see it just looking at that. And I probably should have closed a parenthesis here for the first guy, but it doesn't matter. So 3 times 2 squared. 2 squared is 4 times 3 is 12. 9 times 2 is 18, so that ends up being negative 6. Plus, that's 6. So actually, this is 0, okay? So the answer here is 0. And it's kind of interesting, but if you combine them first, you would get 3x squared minus 6x, because the negative 9x plus 3x is negative 6x. And is 2 a solution to that? I guess it is, because if you have 3x squared minus 6x, you can factor out a 3x and you get x minus 2. So if x is 2, that's 0 right away. So it's kind of nice to see it that way, but this definitely was, I think, the best way of doing it like I did above. So I'm going to erase that just in case. Okay, that got really messy all of a sudden. All right, anyways, let's move on to part B here. Let's see if I can clean this up. Okay, that's fine. It's great. So part B is asking us to multiply them and then just take that of x. So we're not plugging in anything. There's a number instead of x, you plug it in, but if not, you're just doing it as is. So this, by definition, is f of x times g of x. So I've got a little bit of moisture there. Okay, that's fine. So f of x times g of x. Okay, so what is f of x and what is g of x? Again, f of x is 3x squared minus 9x. Whereas g of x is 3x. So really what we're doing is just distributing this into each of those. So we end up getting 3 times 3 is 9, x squared times x is x cubed, minus 9 times 3 is 27, x times x is x squared, and that's it. What's kind of funny is that you can actually factor this, but you kind of get back to where we were a little bit. In fact, if you were to factor this completely, these both have 9 in common you can pull out, and an x squared, and you just have x minus 3. So that's another valid way of writing it, but the top one is fine. Okay, so now moving on to C. So C and D, I think, are the more interesting ones. So here we have composition. Usually students find this kind of difficult idea, but what we're doing is we're taking one function of the other function. So the second one actually will act as an input of the first one. So the definition of this is to write this as f of g of x. So the way I like to tell people is that this O for composition really stands for of. It's the best way of thinking of that. So when I see this, I think out loud, f of g of x. So it's f of g of x, quite literally. G of x is 3x, so this is f of 3x. So f of 2 was replacing all of the x's with 2, like we did here. F of x is just replacing all of the x's with x itself, so you just get the same thing. But f of 3x is replacing all of those x's with 3x. So f of x is 3 times x squared minus 9 times x. So notice, instead of writing x, I'm writing an open set of parentheses. And now inside of those, I'm going to squeeze this 3x, which is replacing our x's. Think of that these x's are all linked. So whatever the one inside parentheses next to the f is, those are that as well. So this is 3x, so these are also 3x. Okay. 3x quantity squared is just 9x squared, actually. You square each of those. 9 times 3 is 27, so that's 27x. And this is 27x squared, because 9 times 3 is 27x squared, good. Minus 27x. And if you wanted to factor this, this is a 27x times a quantity x minus 1. That's kind of interesting to do if you want, but I'm just going to leave it there and stop factoring things. And now this one, well, okay, so this is g of f of 4. So if you wanted to, you could find g of f of x, like I did here for f of g of x, and then plug in 4 into that. But instead, I'm going to take this bit by bit. And just notice by definition, this is f, oh, sorry, not f, but g, there we go, of f of 4. So instead, I'm going to just start from the inside. So what is f of 4? Well, if you plug 4 into f, you get, let's see, I'm going to do it in my head. So we got 4 squared, that's 16, times 3, that's, I guess 48. And then 9 times 4, because again, x is 4 here, that's 36. So I'm going to get 48 minus 36. Maybe I should write it out again. 3 times 4 squared, that's 3 times 16. That's 48. Minus 9 times 4, that's 36. So yeah, that's 48 minus 36, which is 12. So we found out that f of 4 is just 12. There we go. Great. So now we need to find g of 12 to complete this. So how do we do that? We plug 12 into g, 4x. So g of x is 3x, so g of 12 is 3 times 12. Replacing that x with 12. Then we get 36. Awesome. Great, so that was 5. Now let's move on to number 6. All right, so for number 6 here, we're asked to find the inverse function for each of the following. Now, what an inverse function is a function that undoes this function, or these functions. So if you plug in, let's say, 5, for example, you'll get a value, and if you plug that value back into the inverse, it'll spit out 5. So it'll undo what the function did. Okay, and I'll actually show that after the fact, but the method we often use to find the inverse function is to basically let this be y, swap all x's and y's, and solve for y in terms of x, and then replace y with f inverse. In this case, it'll be g inverse. So the first step is to replace f of x with y, simply put. The second step is to replace all x's with y's and all y's with x's. So this is kind of like the swapping step. Everywhere I see an x, write a y instead. Everywhere I see a y, write an x instead. Now the next step is to solve for y. Now this is the most time-consuming step. So to get y by itself, this is tricky because y is in two locations. But what I'm going to do is I'm just going to follow my nose. I'm going to clear denominators. I'm going to multiply both sides by the denominator. So on the left, we get x times that denominator. And on the right, that will cancel with the denominator, and you're just left with the numerator. Okay. And now the only thing I think I can do here is, well, distribute that x. So I'm just, again, following my nose a bit. And now, remember, our goal is to get y by itself. So this, as an equation in y, we need to move all of the y's on one side and all of the x terms, or not x terms, but all the non-y terms, really, to the opposite side. So this y I'm going to subtract to this side, and this non-y term, 3x, I'm going to add to that side. So now, these cancel, so we get xy minus y is equal to 3x plus 2. So it may not seem like we've done anything, because here we had y in two locations, here we still have y in two separate terms, but factoring saves the day. Here we can factor the y out, and we get y times the quantity x minus 1. You can see if you distribute the y back in, you get xy minus y. And then now, to get y completely by itself, we can divide by that x minus 1, and now we have y completely by itself. So now for step 4, we can replace that y with f inverse of x. So f inverse of x is equal to 3x plus 2 all over x minus 1. So let's see if it works. So I said 5 randomly. You can pick any number. And in fact, what you can really do to check it for all values of x is actually compose these. Take one of the other, like we just saw with the previous problem, 5, D and C, and you'll get x. So they undo each other, basically. So I'm just going to show that with the example of 5. So if I plug 5 into f, what do we get? Well, on the top we get 7, on the bottom we get 2. So it's 7 over 2. Okay, so that's not too much fun because it's a fraction, but let's do it and see if we can. So plugging in 7 over 2 into f inverse. 7 over 2 times 3 is 21 over 2 plus 2. So let me try to do it over here. 21 over 2 plus 2. 2 is 4 over 2. You find a common denominator. So that ends up being 25 over 2. So the top is 25 over 2. For the denominator, we have x minus 1, so that's 7 over 2 minus 1. But to get a common denominator, 1 I'll write as 2 over 2. So that's 5 over 2. If you multiply top and bottom by 2 to cancel these denominators, we just get 25 over 5, which is indeed 5. So yeah, gives us back what we started with. Plug in 5 to f, you get a number. Plug the number back into f inverse, you get back the original one you started with. Fantastic. Okay, so now let's move on to part B. That was okay. And this one I actually won't check in the way I checked A, but the steps are still the same. So step 1, replace the function notation with just y. Step 2, swap x's and y's. So x is equal to 4y cubed minus 5. So nothing crazy so far. But then step 3, we want to get y by itself. So this is actually quite nice because y is only in one location opposed to a above. So if you add 5 to the other side, you get x plus 5 is equal to 4y cubed. Dividing by 4 gives you the cube by itself. These cancel. So we get y cubed is equal to x plus 5 all over 4. And then finally, if you cube root both sides, you get y is equal to the cube root of that quantity. The last and final step here, step 4, is to replace y back with the inverse notation. Here it was f inverse because we had f. So here, because we have g of x, it's going to be g inverse of x. Okay? G inverse of x is the cube root of that quantity, x plus 5 all over 4. Fantastic. Now we can move on to number 7. Okay, so for problem 7 here, we're asked to solve these exponential equations. There's actually a few ways of doing this. If you wanted to, you can actually use logarithms to solve these. I'm actually going to be doing this using the one-to-one property of exponentials, which basically says that if you have two exponentials with the same base, but the powers are possibly different, this actually tells you that the exponents actually have to be the same if those powers altogether are the same. So in other words, if you have b to a power equals b to another power, since the bases are the same, then the exponents must be the same. The only exception is when the exponent is equal to 1 or possibly -1, but in fact, for these exponential properties and functions for that matter, we only consider the base to be positive and not equal to 1. So there's no issues here at all. Okay, so I'm going to use that property, but to do that, I need to write these with the same base. So in other words, I need to find a common base. So it's not obvious at first what the common base is, but actually for both of these, it ends up being 3, believe it or not. So I can write 27 as 3 to the third, and I can write 81 also as 3 to the something, 3 to the fourth, actually. So it takes a little bit of recognition to see what you can write things as, but if you just look at powers of 2, powers of 3, powers of 4, that should be enough. Okay? Basically factor the numbers and write them as a power of something until you have them as the same base. So in this case, that works. So notice here when you have a power to a power, you can multiply the power, so we get 3 to the 3x is equal to 3 to the fourth. And then using this property here, we see that the exponents must be equal, so that is 3x must be equal to 4. So then dividing by 3 gives us our solution, x is equal to 4 over 3. Awesome. I'm not going to check this, but if you plug it in, 27 to the 4/3 ends up being 81. And of course, remember, over 3 as a power means you're cube rooting it. The cube root of 27 is 3, and 3 to the 4th is 81. So I'm going to kind of check it. You know what I mean? So now 9 and 243, that is, are actually also powers of 3. 9 is 3 to the second. And 243 is actually, well, if you look at powers of 3, 3 to the 1 is 3. 3 to the 2, that's equal to 9. 3 to the third is 27. 3 to the fourth is 27 times 3, which is, well, you could also think of it as 9 times 9, so it's 81. And 3 to the fifth is actually 81 times 3. 8 times 3 is 24. 1 times 3 is 3. So this is 80 plus 1 times 3, so it's 240 plus 3, so it's 243. Kind of using distribution there, but you get the idea. So we can write this as 3 to the fifth. So now, much like we had here, we can multiply the powers. 3 to the 2 times x plus 2 is equal to 3 to the fifth. So since the bases are the same, we can say the exponents are the same. So I'm going to simultaneously distribute this 2, and I get 2x plus 4 is equal to that other exponent 5. Subtract 4 to get 2x is 1. And then finally divide by 2 to get x is equal to 1/2. And I'll allow you to check that on your own, but that is the answer here. Now, like I said, there is another way of solving that involves logarithms. So I'm just going to kind of casually mention here that if you convert this exponential form, we'll actually see a lot of this in the coming problems in this review, that if we convert this exponential form to logarithmic form, it's log base, so the base is 9, of the result, which is 243, equals the power, remember logarithms solve for powers, x plus 2. Okay. Now, a log base 9 of 243, that's a little hard to do by hand. You can actually use change of base formula, and then subtract 2 to the other side, you get x. So x is equal to -2. And then here I'll use change of base formula. So plus, I'll write this as, let's say, log of 243 over log of 9. And then if you use your calculator, you can actually use your calculator here to find out that this will end up being 5 over 2. And then -2 plus 5 over 2 is just positive 1/2. Another thing you can do is actually use some exponent properties, or not exponent properties, but logarithmic properties. In fact, we can use the power rule specifically to write the top one as 5 times log of 3, the bottom one as 2 times log of 3. Now I'm skipping some detail here, but I'm rewriting 243 as 3 to the 5, 9 is 3 to the second, pulling those powers out as multipliers. The log of 3's cancel, so we see that this is indeed 5 over 2. Okay, and it's positive. I don't know why I would change it to a negative. but that's okay. So then we get negative 2, which is negative 4 over 2, find the common denominator, plus 5 over 2 is positive 1 over 2, just like we got over there. So you could do it this way if you wanted to. I would like to see maybe logarithmic properties like I showed here if you're doing it like that. But notice we still have to write these with the same base in order for these to cancel nicely and doing it by hand. So I don't know. It's up to you really, but I think really the one-to-one property with common base is the way to go for number 7. So now we'll move on to number 8. And with 8, we're going to be doing a lot of this conversion we saw here. So this is a nice transition into 8. So let's take a look at 8 right now. All right, so number 8 here asks us to convert between exponential and logarithmic forms. So here we have a logarithm, exponential, and a logarithmic form. Now this, I think, is probably the easiest question, hands down, on the exam, because all we're doing is just looking between logarithmic and exponential form. But very often, students have trouble with this. So let's take a look to see what's going on. So we have an exponential form is b to the x is equal to y. Okay? And a logarithmic form, using the same letters, is x is equal to log base b of y. In other words, there's a way to convert this form to this form and vice versa. Now the best thing to keep in mind here, and this always helps in my opinion, and I mentioned it in the previous problem as well, is that the bases are the same. And logarithms, I'll just say logs here, solve for powers or exponents. That is probably the best advice I can give you when it comes to converting between logarithmic and exponential forms. So for example, here the base is b, here the base is b. We pronounce this log base b of y. Okay? The exponent here is x, the exponent here is x. The logarithms solve for the exponents, they solve for the powers. So this logarithmic form, converting this to exponential form, the first question is, what is the base? Well, this is written log base, or I guess pronounced log base of 1/16. So the base here is 4. Logarithms solve for powers, so the power of that base is negative 2. And it's equal to the other number I haven't touched yet, which is 1/16. Now another kind of trick people like to do is just swap these two, ditch the log and treat this as a power. And if you swap those, it looks like 4 to the negative 2 is equal to 1/16, again ignoring the log. So that's a nice, I guess, pattern recognition. But as far as explanation goes, this is, I think, the best way of describing it. Because what a logarithm does for us is it finds the power that you need to take this base to get that inside. So this tells us that this base to this negative 2 power gives you 1/16. So logarithms actually solve for powers with that base resulting in the inside. So they're inverse of powers, or inverse of exponents. So this right here is the answer. There wasn't too much work to show, actually, just kind of using this idea, mapping between these two forms. This exponential form, we're going to convert to logarithmic form by doing the same thing. What's the base, what's the power, and then the other one just goes in the missing spot. So we're converting this to logarithmic form. The power will be here, the base is in the subscript. So this is going to be power 1/4 equals log base, the base is 625, of the resulting result of that exponent, which is 5. So that's the answer here. That's our logarithmic form. Okay. Now this is clearly, all of these are true, by the way. So log base 4 of 1/16 is negative 2, and that's because 4 to the negative 2 is 1/16. And you can clearly see that here. So exponentials, I think, are more obvious, just because logarithms are kind of new to us. So that's clearly true. This is also clearly true because 1/4 power, remember, means 4th root. The 4th root of 625 is 5 because 5 to the 4th is 625. So that means log base 625 of 5 is 1/4. Because that's the power that you need to take this base to result in the inside. And lastly, converting this logarithm to an exponential form, the base is 1/3. The power is the result of the logarithm, which is negative 4. And the other number is 81. Again, makes sense. 1/3 to a negative is the reciprocal of that, which is 3 to that. So 3 to the 4 is 81. So that's our answer here. Awesome. So great. So now we can move on to number 9. Right, so here for number 9, we're asked to evaluate these logarithms. Now, this is actually a pretty good question, I think, for each of these 4. They're all kind of tricky in their own right. So, there's a lot of properties that we're going to be using, but the biggest property, I think, is that log base b of x to the r, or let's write it like this. Log base b of b to the x is equal to x itself. So why is this? It's because, remember, a logarithm means that we're solving for the power of this base. It gives you the inside. But clearly, since the inside is a power of b already, the answer is just the exponent of that base, which is x. Okay. So I'm mainly going to be using that idea here. Ln and log have special bases, which I kind of mentioned with change of base formula. But we'll see that soon enough. And what else? There are some other possible properties we can use to do with maybe like the power rule. Let me just write it. Log base b of x to the r is equal to r times log base b of x, which I also kind of showed when we did number 7 a while ago. So the power pops out. And that's true of log of any base. And you can also consider product rules and quotient rules. But we don't really need that here. I may mention it, but I don't think we actually need it. So for A, there are a few ways of doing it, but if I want to do it with this idea in mind, I need to write the inside as a power of 4, and that's kind of tricky. It's doable, but it's kind of tricky. So if I were to write the inside as a power of 4, well, notice really what we're doing is we're calling this equal to x, and then converting this to exponential form, which is another way of doing it, but it ends up being the same thing. So if we're to write the inside as a power of 4, that's the same thing as saying that this logarithmic form in exponential is 4 to the x equals 32. Okay. So with that in mind, if we write this as a common base, 32 I know is 2 to the 5th power, 4 is 2 to the 2nd, so 2 to the 2nd to the x is 2 to the 2x. And then finally, since the bases are the same, we can drop those and equate the powers. Dividing by 2 gives us that x is equal to 5 over 2. So actually, this is 5 over 2. Straight away. And it's because we can write 32 as 4 to the 5 halves. That's what this says. Now that's kind of strange that 4 to the 5 halves is 32, but if you think about it, it makes a lot of sense because 4 itself is 2 squared, and when you multiply these, they cancel, you get 2 to the 5th, which is exactly 32. So there you go. So I didn't really show too much work here, I kind of showed the work here, I guess, but it's okay. Let me actually erase that for space here, but it's fine. Now, ln stands for natural log. It's log natural, I guess. But it's really natural log. Now, the reason why the L and N are in opposite order is because that's how you would say natural log in Latin, basically. So this means log base e of e to the 6th. So right away, using this property, we can basically just cancel these out and just get 6 itself. Perfect. Just using that property. If we wanted to pull the 6 out using the power rule, you can do that as well. But log base e of e is just 1. In fact, log base b of b is always 1. Notice that if the x's are both 1, then you kind of see that there with that property still. Okay. This one, we have log. Just like ln is log base e, log is also a special base. It's log base 10. So for this one, I'm going to write the inside a very special way. I want to write it as a power of 10. Now, I know that 0.01 as a fraction is 1 over 100. In fact, it's kind of in the pronunciation of 0.01. So the 1 here is in the not the thousandths place, I'm sorry, but the hundredths place. Right? Because it's the ones place is 0, and then there's the tenths place, and then the hundredths place. So the way you would actually pronounce this is 1/100ths. So 1 because it's 1, and then hundredths because it's in that place. That's where this ends. So if it was 0.32, that'd be 32 hundredths. So the way to convert that to a decimal, or not decimal, but to fraction, is just writing literally 32 over 100. So 1/100ths is literally 1 over 100. And since 100 is 10 to the 2, this is the reciprocal of that, so that means we can write the inside actually as 10 to the negative 2. Look at that. And now, just like we did above, we can cancel this log base 10 with this 10 and just get the power alone -2. Again, using that property. This property is very useful for this problem. Okay, now here I want to write this radical 3 as a power. We know that radicals are 1/2 powers. That's not difficult to do at all. So we can get our cancellation. We can actually even use this in reverse and bring that 2 in, and thus scoring that 3 to get log base 3 of 3, which is just 1. Right? Log base 3 of 3 is 1. But also, if you cancel these and get 1/2, 2 times 1/2 is still 1. So I like that better, but however you want to see it, this will be 1 in the end. Okay? 27 we saw earlier is 27 we saw earlier is 3 to the 3. There we go. That's what I meant to say. The log base 3 will cancel that 3 to just give you 3. So all in all, we get this is equal to 1 plus 3, which is 4. So this logarithmic expression simplifies to just 4. Okay, great. So that was these 4 for number 9. Now moving on to problem 10 finally. All right, so for 10 finally, we're asked to solve these equations. We have a logarithmic equation and an exponential equation. Now I'll tell you right away that what we want to do is simplify each of these so that they're in the form, logarithmic form or exponential form. Then we'll convert to the opposite form and solve for x. That's really what we're going to do. Now here I need to use the product rule, which I kind of mentioned earlier, but I didn't actually show what it was. And it's because we have an addition. So what the product rule says for logarithms is that if you have log base b of a product x times y, this is equal to log base b of x plus log base b of y. So because we have this plus here, we can combine these into a single logarithm by multiplying the insides, x and x plus 5. So like this. Now if you distribute this, you get x squared plus 5x, which I'll do in a moment, but right now I think it's okay. Okay, and we have equal to 2. Now the quotient rule, which is something I also mentioned but didn't write, is division on the inside corresponds to subtraction on the outside. So similar, but a little different. Okay, so now this is in logarithmic form finally, 1 logarithm. So now we can convert this to exponential form, the other form. So in converting, we see that the base 6 to the power 2, where bases are the same and logs solve for powers, is equal to the inside, and now we'll distribute this and write this as x squared plus 5x. Perfect. Now we know 6 squared is 36. Subtracting that to the opposite side gives us a quadratic in this kind of standard form we're used to. X squared plus 5x minus 36. Now since 36 is 9 times 4, and the difference between 9 and 4 is 5, this actually factors as x plus 9 times x minus 4. Meaning that x is either equal to the opposite of that or the opposite of this. So I did that kind of fast. The factoring part I definitely did fast, but the two numbers that multiply to negative 36 and add to 5 are indeed positive 9 and negative 4. So allow you to think about that for a little bit, but that's that. Now, one of the biggest tricky spots here with 10a is that these logarithms cannot have negative insides. Any logarithm cannot have a negative inside because since the base is positive, right, because our bases are always, again, positive and not equal to 1, then a positive number to any power will be positive. So there's no way a positive number to a power can result in a negative. So essentially these insides can always be, must always be positive and not 0 also. So if you had a value for x, then when you plug it back in to check your answer, if a resultant is 0 or negative inside of a logarithm, it is an extraneous solution. Now that actually happens here. When you plug in negative 9 right away, you get log of a negative. So why is that the case? Well, it happens because if you were to plug negative 9 here, you get negative 9 and here you get negative 4. Negative 9 plus 5 is negative 4. Now multiplying those insides, negative 4 times negative 9 is positive 36. So this statement still makes sense. But because we combine these into 1, we're assuming these were both positive, so that this result is positive. But notice if they were both negative, the result on the inside could still be positive. So that's a tricky spot for logarithms. So you want to make sure you check your answers and that you do not get an inside of a logarithm that is negative. So here this negative 9 results in a negative inside, so that is an extraneous solution. 4 is actually okay, Log base 6 of 4, that's positive. Log base 6 of 4 plus 5 is 9, that's positive. And 4 times 9 is 36. Log base 6 of 36 is 2, because 6 to the second is 36. So that works out. So our only answer here, actually, after checking for extraneous solutions, is x equals 4. Perfect. Now, this one is a little tricky. There are a few ways of doing this that are interesting, but I'm going to show you the way I would do this. I'm just going to take ln of both sides and then go from there. I'm going to solve for x by using power rule to bring powers out of the logarithms, which again I'm using ln. I could use log or even log base 6 or log base 10, but ln is just less to write, and I'm going to be writing it a lot the way I'll be doing it. And as a bonus, I may show a kind of other way, alternative way of doing this one as well, which I think is also kind of nice, but not needed. Now, the only problem is that there's a lot of symbols, a lot of things are going to be, it's going to look really messy. So if you want to approximate as you go along, I don't mind you approximating. I didn't specify. Normally, if I wanted to approximate it, I would specify. Here I didn't. So as is, I would want it as an exact value. But because it gets messy, you can actually approximate as you go along. So let's see what I mean by that. So the first thing I'm going to do is I'm going to take ln of both sides, which is allowed. So I'm going to take ln of the left equals ln of the right. And then I'm going to use the power rule to bring the powers out as multipliers. So that x plus 4 is multiplied to ln of 6, which is just a number. And this x is multiplied to ln of 10, which is, again, just a number. Now, if you want to use your calculator to evaluate these, you'll get some weird decimals. And then you can distribute and solve for x like that. And that's okay if you want to do that and approximate as you go along. Just be pretty generous with the approximations, maybe like 4 or 5 places, something like that. But here I'm going to not do that. I'm going to keep it exact. So you'll see what I mean. So let's distribute this number into this. So this is ln of 6 times x plus 4 times ln of 6 equals ln of 10 times x. So it's a number times x plus a number equals a number times x. We want to get x by itself, so I'm going to move this x term to that side and subtract. So I'm subtracting ln of 6x to this side, ln of 6 times x. Here, these cancel on the left, leaving us with 4 ln of 6. These subtract as follows, ln of 10 minus ln of 6. And that may look a little funny at first, but just remember, like, for example, 5x minus 2x is whatever 5 minus 2 is, which is 3 times x. Also, you can distribute the x and see that you indeed get ln of 10x minus ln of 6x. But now, to finally finish this in solving for x, we can divide by this quantity, which is multiplied to x, ln of 10 minus ln of 6. So that looks really weird, but that is the answer. I'm going to write the answer here, and I'm even going to simplify it because we can, using some properties that I've kind of been talking about. There's a lot of properties we can use. So this is the answer. So you can box this, and that's fine. If you want to approximate this and verify that you get the same result more or less, again, depending how accurate you were as you went along, because honestly, approximating as you go along in an equation is generally not advised, but I'm trying to be lenient here because there is a lot otherwise if you were to do it this way. Now, I'm going to try to combine these and simplify in some way using some properties we've seen. So first off, that 4 I can bring in as a power. 6 to the 4th, by the way, is 1296. Here, this is ln of 10 minus ln of 6. So we mentioned that if you have subtraction, that's a log base, whatever the base is, of the quotient of those numbers. So this is actually ln of 10 over 6. And notice 10 over 6 reduces actually to 5 over 3, so that's nice. So this is ln of 1296 over ln of 5/3. So that's a nice way of writing this. And in fact, you can go a little further. Now, if you wanted to approximate this, this would be the last part where you would approximate. Because you could go a little further, actually. This, I think, is maybe a little showing off, kind of. But at least it shows the change of base formula that I mentioned before. And that's a way you evaluate a logarithm that doesn't have a base of 10 or e. So ln of 1296 over ln of 5/3 is equivalent, by change of base formula, to log base 5/3 of 1296. So this is another alternative form for x, which I think is nice and probably the best way of simplifying this. Now, I'm going to, as a bonus, the next screen, redo this problem in a different way that'll give us this answer basically right away. So let's take a look at that right now. Okay, so I've actually erased everything we had in the previous board except for the answer we got in this weird form. And I'm going to show you there's actually a way to simplify this so that this converts right away to this logarithmic form. Kind of weird, but it works. So what I want to do is I want to get this in the form something to the x equals something. So blank to the x equals blank. In other words, I don't want two exponents involving x on the same side. So what we can do actually is, well, first off, we can split this up. 6 to the x times 6 to the 4th. And then we can divide both sides by that 6 to the x so that we only have x's on one side, but as powers now. Notice 6 to the 4th is 1296. And this is 10 over 6, which is 5 over 3 to the x. So that actually wasn't too much work, and right away we see that this exponential form in logarithmic form is exactly this. The power x is equal to log base, the base is 5/3, of this. Fantastic. And then if you actually wanted to use your calculator to approximate this using change of base formula, you can take ln of this over ln of the base, or you can use log as well. So I'll use log just to kind of change it up. Log of 1296 over log of the base, which is 5/3. And I'll actually do this not off screen or anything. I'll do this in my calculator just to show you what I get. And I'll actually show you the screen and all that. So here's my calculator. I'm going to type in log. Log is somewhere over here. There we go. There's log and ln. Remember, log is base 10, ln is base e. And actually, if you zoom in, you can kind of see that above this is a 10 to the x, above this is an e to the x. And it'll always be like that basically on any calculator. Okay, so I'm using log here. So I'm going to take log of 1296. You may want to use parentheses, but for my calculator, it doesn't actually make a difference. If you get a different value than I get, then you may want to use parentheses just to be safe. But you should get this value. So log of 1296 divided by log of. Now for this guy, I need to write this in parentheses because it's itself a division. Otherwise, the calculator is going to do something funny like log of 5 and then divide that by 3. But we'll want to do log of 5 over 3 as a quantity. Okay. So let's press enter and see what we get. So this is our answer. So it's 14.030. So let me write that down. This is about 14.030. Actually, the number after that's a 3, and then 0, then 221. So about to 4 decimal places, it approximates to this. So if you try doing this the other way I showed before this, which I think this just looks so much cleaner actually. But if you try to do it that way and approximate as you go along, as you went along, you should have got more or less this. Now, if you were off by a bit, that I don't really mind too much because again, you're doing a lot of work in showing it that way. But this definitely makes it look so much cleaner. So I may prefer you actually to just do it this way. But again, it's up to you, whatever you find easier. I'm showing you everything in as much ways as I can. So I wish you luck on the exam, and with that being said, that concludes our review.